The typical high-energy colliders can approach to the GeV to the TeV scale, but there are also the many ultra-high-energy scale in the theoretical and the observational point of view. And today I want to talk about such ultra-high-energy scale beyond the TeV. The first one is the ultra-high-energy cosmic ray coming from the universe, and the second one is the heavy scale of dark matter. The ultra-high-energy cosmic ray is often called the UHECR. The typical scale is given by the peta-electron volt 10 to the 15 electron volt, or extra electron volt 10 to the 18 electron volt. This is extremely higher than the LHC. And the cosmic ray is composed by mostly the proton or charged particle like as nuclei. So if the UHECR comes from some unknown astrophysical sources and it collides with the atmosphere of the Earth, then the air showers of the secondary particles arise, and this makes this comes from the collision between such a proton and nucleus and the air particle, and we can evaluate the scattering cross sections. There are many candidates for this UHECR as the astrophysical sources, like as the active galactic nucleus (AGN). At the center of the galaxy, some dynamic galactic nucleus is possible, and the gamma ray burst in short time, briefly the GRB, and the star burst and the formation can be the sources of such a UHECR. And because these particles are charges are on the magnetic field, so the directions of the UHECRs are bound along the magnetic field. And especially such a UHECR can generate the secondary particles as the neutrino with the peta-electron volt to the extra-electron volt Q. Such a UHE neutrino can be produced by the two different regimes. The first one is astrophysical accelerators. From some specific astro obstacle, the protons with higher scale can be produced, and the proton-proton collision can make the mesons like the pion, and eventually it indicates the muon and the neutrino. And the other possible regimes is for the productions of the UHE neutrino is the cosmogenic neutrino. If the UHECR proton collides with the CMB proton during the propagation, then this makes the pions and again the muon and the neutrino generated. So this is called the GJK process, and also the ultra-high-energy scales of neutrino can be produced. And such a peta-electron volt to the extra-electron volt scale of the neutrino can be detected by the huge detectors like as ice cubes in the Arctics. And but the problems of such ultra-high-energy cosmic ray is still there are deviation between theoretical model and the observational one. So the possible sources like as the active galactic nucleus, the number of the AGN is too small, and it locates very anisotropic in the positions of the universe, but the observation of the UHECR is too isotropic. And the typical model of the AGN and the GRB assume that the dominance of the proton, but the observational data is compatible with the more heavier nuclei composition. So we need a new model for the AGN and the GRB, And the standard model of the AGR and the GRB and the produced UHECR predicts the axial electron bolts of the cosmogenic UH neutrino, but there was detection in the ice cube. So if we draw the ground neutrino spectrums beyond the G with the TB over the NS scale and as a unit of the blocks, then this line is the predictions for the atmospheric neutrino, and such atmospheric neutrino can be detected by the ice cube from the TB to the beta electron volt. But in the observation, there is the ice cube upper bound, and it makes the deviation with the prediction. There's no access in the realistic data, so the standard model of the AGN and the GRB is this fiber. So the such AGN and GRB is the not clear sources of the UHECR, and the new model is required. The second topic is the Harvey dark matters with very wide ranges from the composite dark matter to the primordial black hole. The first one is the super heavy dark matter with the scale of the 10 to the 10 to the 10 to the 19 GB. This is the quite heavy compared with the WIMP scale. The WIMP assume that typically the GB to the TB scale. So such a super heavy DM is called the WIMP-zilla. This is not produced by the thermal scenario. Rather than that, the super heavy DM is produced by the lating after the implantation. Because the dark matter scale is quite large and reach to the lating temperatures. So after the production of such a super heavy dark matter, this can make the UHECR from the early universe, but the observational UHECR corresponding to the super DM is not detected yet. And the second category of the heavy dark matter is the composite particle rather than the elementary dark matter. We can assume that the QCD-like structures in the dark world, for example, the QCD light is again. Now the mass reached to the Planck scale, 10 to the 19 GB, or the 10 to the 12 gram. Almost the radius, the size of dark matter is the asteroid, so this is the quite microscopic size. And also we can assume that the additional QCD in dark structures. Such QCD-like interactions makes the bound tight, so the composite dark matters can be possible. The third category is the primordial black hole, so-called the PBH. This is the quite compact object. The mass scale is around the solar mass. Such a PBH is assumed to be the bomb in the early universe with the density perturbation. But there are several constraints like the gravitational lensing and effects of the PBHs on the CMB and the gravitational wave produced by the PBH mergers. So the current status of the PBH is that the PBH cannot be the bull dark matter. This can be the only subdominant one. Such a heavy dark matter strongly interacts with the gravitationally, so unlike the dark matter direct detection, they use the already I mentioned that the constraints of the PBH. Usually this can be detected by the gravitational lensing or structural formations through the density perturbation and the CMB probe. The final category is the dark star. This is the quite heavier than the solar mass. The mass scale is 10 to the 2 to the 10 to the 6 solar mass, and the size is the radius of the 1 AU. There might be some exotic complex objects, and such dark star can be powered by dark matters and the normal matters. So in the remaining time, I will focus on the primordial black holes with the quite simple formula. There are several quantities in the primordial black hole. The mass scale is determined by the formation time of the PBHs in the early universe. By the dimensional analysis, the PBH mass is proportional to the time. So at the when the model black holes formated in the 1 second in the early universe, then the mass scale is around to the 10 to the 5 solar mass. So the earlier PBHs remain at the light mass. And also we can calculate the density contrast for the PBHs. If the process is smaller than gravity, then it survives the collapse and eventually go to the black hole. And the radius of the PBHs is given by the relations with the mass from the Schwarzschild black hole of the general relativity theory. So for the solar mass scale of the PBH mass, the size is around 3 kilometers. And from the Hawking temperatures, the temperature of the PBH is inversely proportional to the its mass, and we can calculate the evaporation time by the Hawking radiation. Then the lifetime of the PBH is the 10 to the 67 seconds for the solar mass scale of the PBHs. So to exist the PBHs, it should be the rather than the 10 to the 15 gram. So the below the 10 to the 15 gram, the PBH is already evaporated, so this cannot be the dark matter. And the another low one is 10 to the minus 5 gram. This corresponds to the Planck scale. So the formation time of the PBH is the approach to the Planck scale, so that it cannot be formed before that the Planck scale. And also there are the other ranges, the evaporating window from the 10 to the 15 gram to the 10 to the 17 gram. This is called evaporating window because in this mass ranges the PBH is evaporate to the X-rays or photon and the neutrino. So such X-ray excesses are not observed. So in this mass ranges, the fractions of the PBHs should be very small. And also there are other mass ranges from the 10 to the 22 gram to the 10 solar mass. This is called the lunar stellar mass. In this case, in this mass ranges, effects on the CMB and the gravitational lensing, so the fraction of the PBH also should be very small. So the full fraction is already ruled out. And above the 10 solar mass, this is supermassive mass ranges from the 10 to the 5 solar mass. This mass ranges produces the gravitational wave, so already also the ruled out, only the subfraction is possible. And such a 10 to the 5 solar mass upper bounds comes from the formation time correspond to the 1 second. The formation later than the 1 second can interrupt the cosmic history, so that this is the upper bound. So only the viable space to gives the full fractions of the PBHs. The still remaining window is 10 to the 17 gram to the 10 to the 22 gram. This window is called asteroid mass ranges, and they're very hard to constraint, and still not ruled out for the full fractions. So today we talk about the very high energy scale from the ultra-high energy cosmic ray and the neutrino. They can be arised from the active galactic centers or the gamma ray burst, but the typical model cannot explain the observational data, so these are not still clear sources. And also we discussed about the heavy dark matter, with the very full ranges from the superheavy dark matters or composite dark matters, primordial black hole. And in the many mass ranges of the primordial black holes, many windows are ruled out from the observations data, like as X-ray, CMB, or gravitational wave, but there are still viable very narrow mass ranges for the full fractions of the primordial black hole.